Today I'm going to talk how we transform CloudMR into a serverless and scalable cloud-native ecosystem. I don't have anything to declare. So in our field, it's very common that two researchers found each other and come with the idea of a new coil, and they go to their own laboratory, but they decide to build a coil anyway. And they scan it, and then they see the images, and there is a lot of SNR. The images are fantastic. They write grants, publications, but this is not the usual story. A lot of coils end up in the shelf. And this is a spare of resources, time and money, and also you need to have a scanner in order to evaluate the performance of these coils in terms of SNR or SAR. There are available software that give you an idea of the performance of this coil, but their scope is usually very narrow. The integration is not well made. It's difficult to model the interaction between a body model, and a coil. And most of the code is done by researchers, which are not always software engineers, so they might lack of documentation and architectural constraints. The classical thing, oh, it worked on my computer. So a decade ago, Riccardo Lattanzi, my PI, came with the idea of gathering all the available open source software of MRI and create web-based framework for SNR optimization that doesn't need any scanner or coils, with the idea of simulating the entire MRI setup and eventually democratize the MRI research. So for these purposes, we gather departmental resources like softwares and data, come MRI as a block equation. Carlos is going to talk about that in the next section. The virtual human project models, my favorite toolkit, VTK and ITK, sequence generation like PulseSec and MTrack, Anais knows better about that, NIVU, Marie for field simulation, and BART for image reconstruction. Martin and Daniel are going to present in the next section. And we build 6 web applications. So Camry, that generates synthetic MRI images, DGF, that simulates coil behavior for simple shapes, Mr. Optimum, that is able to calculate SNR, Test to calculate temperature from SAR, Poirot, that evaluates the SNR versus the intrinsic ultimate SNR, and Rado for the radiomic pipeline. So for the first implementation, I had a previous experience on a project where we were calculating radiogenomics on a multi-center data, and I transferred the same concept to CloudMR. So I built a main system, which was simply a LAMP machine, Linux, Apache, MySQL, and PHP, that take care of the information of the user and the tasks, and a computing unit that query this database and slowly calculates and update the database. For example, the SNR calculation. But this was available only in the NYU Langone LAN. And in order to give our service to the internet, we need to go cloud. And so for these purposes, I got inspired as a biomedical engineer from the human motor system. When you want to move muscles, from the motor cortex starts efferences that reach a particular spinal node. And from that, the lower motor neuron is going to bring afferences to the muscles that eventually starts moving. As then it starts moving, the lower sensory neuron is going to send feedback to the same spinal node and then reflect back to the sensory motor cortex. So in this way, we can think about the muscle as the SNR calculation or Camry, the simulation of the K-space. And the spinal node is simply a service that takes care of the input, validates it, and gather the output. And the brainstem as a way to allow user to send APIs from the front end or from computers. And the cortex is basically the main system that I developed in the previous version. So for this reason, we hosted the cortex on a website, and we created an EC2 machine in our AWS account. I set up a cluster of Kubernetes, and then I start building the brainstem pods. And for every application, we had 4 pods. The interesting point is that we have a persistent volume that was mounted through all the services, so that we didn't have to move through the internet all the data when you're moving through the services. When we added the second application, Test, we realized that we were doubling a lot of these pods, but in this case, we were also doubling the cluster size that became a problem because it duplicated our costs. So we took a step back and we tried to see if we could optimize this architecture. In this roaring more interested about the serverless modernization. And for this reason, we realized that the idea of an endpoint that trigger some calculation is actually available on Amazon with something called API Gateway. And all the queuing system, input, output, and error managing can be completely replaced with Fargate and Lambda function, which are basically Python code or any kind of code that run on an abstraction of the architecture behind. And the front end doesn't need to be in a pod, it can be spun into Amplify, which is a serverless server. The persistent volume was swapped to an S3 bucket, and therefore we could completely delete our cluster and turn off the EC2 machine. That was the most expensive part of our architecture. And eventually, we also brought inside this environment our main system using Beanstalk and Route 53. So this immediately changed the price, the cost of our architecture, reducing the cost of 81%. We were spending something around $1,300, and eventually we end up to $200 per applications, $100 per application, to be fair. So our architecture is very simple. So the main system remains in our AWS account, but it's spin on Aurora MySQL database and Beanstalk. And we offer the way to interact with it through API Gateway that can be connected directly from the front end or from API. Then we have a route for the data handling, downloading and uploading. And then when a user wants to schedule a task, let's say an SNR calculation, they are going to send an API either from the front end or from the computer. And the payload will be analyzed by the task Lambda function. And after be validated, we'll start a state machine that as a first state decide whether run on a Lambda function or on a Fargate instance. Of course, it is going to have some logic behind, and the logic is usually if the calculation takes more than 15 minutes, it will run on a Fargate. If it is fast enough, it can run on a Lambda function. But both of them share the same code, and after the calculation, the results will be uploaded into buckets, results and failed in case he failed the calculation. And the action of uploading something on this bucket is linked to a trigger of the update function that reads the file and then update the final database. So in order to use this architecture, we have to restructure our repo for each application. So for every application X, let's say Mr. Optimum or Camry, we have the Web GUI repo, where we have the website in React, Redux, and Nivue. And then we have the X tools, which is the real code. So it's a Python, MATLAB, or even a Docker that runs into the Fargate and then the Lambda functions. And then we have the X app, so Mr. Optimum app, Camry app, where we have a description of the architecture as a YAML and all the API definitions for the application. So let's talk about the mods and how to interact with these apps. We describe 3 different usage, we call mods, of our application. So the mod 1, Cloudemar execution, is for user who wants zero installation and simply access to the apps, so calculates the SNR. The mod 2 is for labs that request many calculations, and so they might saturate our free tier. And then the third mode is the local Python execution, where a user can is mostly for power user, and user can use it offline and develop algorithms. So in the mod 1 idea, the users log in cloudemarapp.com or one of our apps, schedule jobs, visualize them, and the computation run on our AWS account. While the mod 2, user download the /app part of the application and spin them in their own cloud, and the calculation will run on their own account. Cloudemar simply acts as a metadata observer, UI provider, and result indexer. And the mod 3 remain where user can use our Docker packages or our Python packages, and the code is the same of the other mods, but user can integrate them in their own tools, and they can also edit it. So I'm going to present 3 applications now and the way you can interact in the mode 1. So Camry is our web app that emulates the MRI experiment by numerically solving the block equation and generates multi-coil K-space data entirely in the cloud with no manual file handling. It takes mtrack and pulsex as a sequence descriptor. Marie pre-simulated field, CoMMRI is used inside as an engine for the block equation solver, and BART and CloudMR as image reconstruction. They work all the same. You can log in the application. You have 3 tabs: home, setup, and results. In the home, you have all your file. In the setup, you can configure your calculation, which is the K-space calculation. So this is an old version of the front end we present in SMRM, but we are working on a new version. Here it's only based on the Duke 2mm body model that is pre-simulated with Marie. And then user can select the type of sequence they want to apply to this model. It can be mtrack or pulsec, thanks to Anais. And we can queue job. And by clicking queue job, it starts the calculation in mode 1 in our account. In mode 2, it will run in your own account. As you can see, I'm not that good in giving aliases, but in a couple of seconds, you are going to get the bidimensional slice that you just configured, and you can either download it or visualizing it in the web app. Is happening? Yeah. And by clicking play, you can see it. It will appear a new panel where you can visualize the results and interact with that. So this is a root sum square reconstruction of the image, and this is the real output, so the K-space. In this case was a single coil K-space. And we also give an SNR evaluation of the sequence. But the real application for the SNR is Mr. Optimum, is our open source web-based tool for SNR estimation. We allow 4 types of calculation of the SNR. So multiple replica. If you have repeated acquisition of the same K-space, we can calculate the SNR as the mean through the replica subdivided by the standard deviation. We also allow analytical method, the Kalman method. It uses, you need to have a signal and a noise file for the calculation, and use the coil sensitivity and noise covariance to weight the reconstruction so that the image that you see is actually built in SNR units. Then we have pseudo-multiple replica that using a signal and a noise, it adds realistical scaled and correlated noise to the K-space and reconstruct many replica in a Monte Carlo simulation and compute voxel-wise SNR from the standard deviation across the replicas. And generalize pseudo-multiple replica, which is a faster way of doing pseudo-multiple replica, where the noise stats is taken from the replica, but also from the neighboring of the pixel-wise SNR, given a window. So the application works similar to Camry. So we have the 3 tab: home, setup, and results. With the setup, you need to upload or select the signal and the noise, and then you can decide which kind of analysis you want to do on this data. For example, here is the analytical method. You need to select which reconstructor you want. And in this case, I'm showing how to mimic a sense acquisition from a fully sampled K-space in this case. And then you simply click QJob with an alias, and it's going to start the calculation. And so you can go on the result tab, and you can either download or visualize the results. If you decide to download it, a zip file will be downloaded on your computer, and there will be a JSON file that describes the file inside the zip file, the MATLAB file that you can load on MATLAB, and the Nifty file for that we use on the calculation that are shown in the image, in the web, in the front end. Here at the SNR, but you can see the coil sensitivity that we used for every coil, of course. But you can also see G-factor, the inverse G-factor. And you can draw region of interest to visualize your results and inspect them. And you will see the histogram changing right away into the histogram visualizer. You can upload, save your region of interest and use it in different pipeline because it's a simply Nifty file. So I'm going to present the last application, so TESS, which is our MRI RF safety web app. TESS estimates the SAR depending increase in temperature given by a SAR application, and it's simply solving the bioheat equations. Of course, the bioheat equation needs the SAR, but also many other settings that you can configure on the setup of the application. So here I'm going to start populating the requested variables for the bioheat equation. So of course, the tissue density, the blood perfusion, the heat capacity, thermal conductivity, and the metabolism. And they are all nifty files, and they can be of different resolution, different size, but they will be cropped during the calculation according to a mask, if you want to pass a mask, or to the tissue density. It will be done, made all behind the scene from our /tools package. When you finish this, you can customize the simulation parameter. So for example, the initial temperature of the simulations, the SAR that you want to apply, and for how long you want to apply. And then you customize the blood temperature, the blood capacity, the blood density, and the temperature of the air. And then you can queue in the job, or you can visualize, since these are three-dimensional data, if we are capable of reading correctly your data, to check, like a sanity check, you can see exactly how we will interpret your data to see if it has a mismatch between your three-dimensional array and how we will interpret. So then you can click Queue Job, give in an alias, and we'll start the calculation in mode 1 in our AWS account, in mode 2 in your own. Then you can go on the Result tab, and you can see the result table. You can visualize it or download, of course. It will be similar to the one on Mr. Optimum. And then the View Result panel we're going to open, and you will see the final temperature that we estimated, in this case, after 50 seconds of applying that SAR. You can also see, for debugging purposes, also the maps that we used for the calculation, just to check if everything is correctly as expected. And then you can visualize in different way your results. You can see the three-dimensional surface, you can see a coronal cut, a sagittal cut, you can slice to it, you can zoom, you can see complex and values in case it is for Mr. Optimum, for example. You can change minimum, maximum, the color bars, you can take screenshots to use in publications. Yeah, and of course you can also draw region of interest in the same way, saving them and uploading them exactly as we did with Mr. Optimum. So here you can see the raw histogram changing. Yeah. So let's talk about the Mod 2 now. So Mod 2 delivered the same user experience as Mod 1, but everything happened inside the user account cloud. So the front end of the computation ran entirely in their own account, and user control cost, security governance, and scaling. Cloudemar used only reads metadata for indexing and result listing. And this is a good mode if you want to develop something and see how it would scale into the cloud. And you can develop this using the Mod 3. The Mod 3 is the local Python tools. It uses the same core algorithm as the Mod 1 and Mod 2, but it runs securely on local and offline. And it is ideal for if you have protected dataset or you want to run it on HPC cluster, for example. But my favorite part is that you can use it to develop, because you can prototype locally on your computer in the language that you prefer, and then integrated it into the Mod 2 or the Mod 1. So let's talk about the /tools part of our repo. So here you can see our repo Cloudemar, which is the image reconstruction, noise assessment, and image subsampling. On the top right of the image of the slide, you can always see a QR code that is going to bring you to a collab, Google Colab link, where you can actually see exactly what I'm doing and trying on your side. The installation of our package is very simple. Just pip install and the URL, cold install the URL, and this is the short, tiny URL in case you want to follow it. You will end up in our package. You can click on the notebook, and then you can run it, you can play with it, very simple. So the reconstruction classes that we developed for CloudMR are 9, and they all hierarchically inherit from the base reconstruction classes, where we have the input-output management of the signal and the noise and all the needed data. We read a three-dimensional array, NumPy, where in the first direction you have the frequency, phase, and the coil. So if you want to do a simple root sum square reconstruction, what you have to do is to import the class and then instantiate it, and then set the noise, set the signal, and with the method getOutput, you have the image. Here is an example of the k-space of the signal, the noise, and you have the RS reconstruction pre-whitened. Because we also give information on how to use the noise, you can easily get the noise bandwidth, the noise covariance, the noise coefficient, or pre-whitening any kind of data. If you want more complex reconstruction, we also offer matching filter called combination reconstruction, B1. In the same way, you need to import the class, instantiate it, set the signal, set the noise, set a reference k-space that you want to use for the call sensitivity maps calculation, or your own call sensitivity maps. And then with the method getOutput, it will be contextualizing this kind of reconstructions. And so you will have access to your call sensitivity maps, automatically masked, and the B1 reconstruction. We also offer accelerated reconstruction, here an example with Grappa, and similar to what I showed in the web app, you can mimic an acceleration bidimensionally, and then instantiate the class Grappa, and then set the undersampled signal, the acceleration, the auto-calibration line, the noise k-space, the Grappa kernel, and the reference k-space, and then you will have a Grappa reconstruction. This is how it looks, our k-space of the force coil, for example. Similarly, we also have sense reconstructions. And the interesting point is that all our classes are hierarchically built. So you can apply polymorphism or morphism, and you can morph a sense reconstruction into a sense one. In this way, everything has been pre-calculated for the image reconstruction, will be used for the G-factor class. And in this case, the getOutput will be contextualized in the context of the G-factor. And therefore, you can have images like sense reconstruction you see here, the G-factor, the inverse G-factor, and the automatic masking that we are using. If you want to add a new reconstructor, it's very simple. You just need to select from which class you want to inherit the methods. For example, if you want to inherit it from the RSS reconstruction, you can simply instantiate the class and extend it, and then change it, for example, only the getOutput method. In this way, you will have all the framework working for you, and so you can instantiate your new class, set the noise, set the signal, and the getOutput will trigger your own getOutput method. And in this case, you get this reconstruction. That doesn't make any sense, but this is not the purpose of the talk. But this is a good way to see how simple it is to create something on Mod 3 and then immediately integrate into your Mod 2, because by changing a couple of lines on the YAML file that we give, you can spin your own new reconstructions. And in the future, we hope we are going to deploy a way that allows you to bring your reconstruction to the community, so that also in Mod 1, so to the broader public, can be used. Mr. Optimum/tools is our package for the SNR calculation. You can always follow the QR code or the tiny URL if you want to try by yourself. And it's installed in the same way. Pip install, conda install with the URL. The SNR calculation depends on the reconstructions. So for the reconstruction part, of course, we use CloudMR tools, while for the real SNR calculation, we use Mr. Optimum. And the output will always be an SNR maps. This is how we can create a calculation of analytical method Kelman for a root sum square reconstruction. We just need to import the class, instantiate it, set the noise, set the k-space, and then clicking the get output method. As you can see, they follow the same concept of CloudMR tools. So you can also morph image reconstruction into a sense reconstruction without calculating back all the other variables. And this is what you get. You have an image of the k-space, of the SNR. This is an example of pseudo-multiple replicas. So you need to import the class pseudo-multiple replicas and the reconstructor, of course. So you instantiate the class, you instantiate the reconstructor, you set the number of replicas you want to simulate, and then set in the noise, set in the signal, attach the reconstructor to the class, and then clicking the get output method, you will have the SNR. Similarly, with the generalized multiple replicas, with the only difference that you can use less replicas because the information of the noise is taken from these sliding windows through the image. And so you need to define a box size of this windowing. And multiple replica that allows you to have, it expects to have a replicated acquisition of the bidimensional k-space. So the input will be a 4D matrix, 4D array. And so you instantiate the class, you instantiate the reconstructor, you set the noise to the reconstructor, and then you can attach the reconstructor to the SNR calculation class. And then you can simply call add to the k-space to the class, and clicking, and by using get output method, you actually get the SNR. This is how they look, these images. So you have the analytical method here, RSS, the pseudo multiple replicas, the generalized multiple replicas, and the multiple replicas. So what's next for CloudMR? So in our work, we all build complex pipelines, and the traditional approach, which is manual, needs to manually transfer between disconnected tools. And it's slow, repetitive, and with a high risk of error and data inconsistencies. So in CloudMR, the idea is to build pipelines, which allows you to go end-to-end from a coil mesh to the SNR. This is the original idea of Ricardo. And it managed automatically the data flow and automatically convert the data according to the input of each software. For this, we did this by using standard software and APIs. So we have Gmesh for coil modeling, for example, MRI for the electric simulation, MTRAK and PulseSec for pulse sequence design, Camry for k-space simulation based on MRI, BART for image reconstruction, Mr. Optimum for performance evaluation in terms of SNR or G-factor. This will allow us to have this framework where you can take any body model, eventually morphing with real data, patient data, and then virtualize a coil, and then simulates with MRI runtime the electromagnetic fields, and then perturb your simulation with MTRAK and PulseSec, and then passing this information to Camry that is going to solve and give the output, which is the k-space, like a virtual scanner. And then there will be all these second level applications like TESS, Rado, Mr. Optimum, Poirot, and BART that can take this k-space and transform it in images, for example, with BART. And with this, we will have a third layer of application where you can have, for example, a data loader that takes the images and allows you to do all your downstream application for deep learning or radiomics, and having possible images of healthy patients, for example. Mm-hmm. But on the other side, the most important part, I think, is for RF coils design, where you can change the hyperparameter of your problem and try to optimize it to find the best solution to give you the best SNR. So in conclusion, CloudMR is a fully modular serverless architecture that enables simulations, reconstructions, SNR calculations, safety assessment, and radiomics pipeline all in one ecosystem. Moving from server-based to serverless cloud computing resulted in 81% cost reduction, making the architecture sustainable and scalable for the community. We offer these three modes to interact with our web apps. So mode 1, no installation, just the app. Mode 2, user control deployment. Mode 3, local development of algorithm. And CloudMR is a growing open source environment for sharing methods, comparing reconstruction, and rapidly translating new ideas to entire community. And this is done by bridging resource prototyping, cloud scalability, and community adoption all in one unified code base. Thank you so much.